Hello everyone. This is a new day. Um, let's see, it's September the 3rd. Alright, it's not in the morning because today I have some issues to deal with in the morning, so I kind of delayed a little bit. Let's go right into it. Erect the fence. Yeah, I don't know. I was talking some jerk. I don't need an opening. Come on, I just start doing it. Every time I try to make something up for the opening. You're given an array, tree. Oh, interesting. Represents the location of a tree in a garden. Okay. You're asked to fence the entire garden using the minimum length of rope, as it is expensive. The garden is well fenced only if all the trees are enclosed. Return the coordinates of trees that are exactly located on the fence parameter. So I need to fence the entire thing with the minimum length of a rope. What does it mean by fence? Just put them together. Well, is it curved or everything is going to be like a square? Yes. Well, fence only if all the trees are enclosed. So that means to fence this, wait, what does it? All the given points are unique. Hold on a second. How do we fence? Like, but why is this one not on the fence? I cannot go like, it's a rope. Can I go this way? This way? Then why 2, 0? Oh, it is. So we start from here. We go this way, and then this way, and then boom, boom, and down. So it's 1, 1, 2, 0, 3, 3, 2, 4, 4. Ah, I see. I see. This one will be just all of them. 4, 2, 2, 2, and 1. No order, right? I didn't talk about order. Okay, that's fencing. Okay, so this is like what? This is like a support vector machine, right? You want to find the ones that are on the edge. You don't care about anybody else. Okay, so what we can do, to begin with, everything to the most left, to the most right, to the most top, and to the most bottom, they must all be included, right? Because they are the anchor point. So we can just do a, I think finding this is the smallest on the first one. This one will be the smallest on the second one, the biggest on the second one, and the biggest on the first one. So I can find 4. So we can box them, right? We'll box them up. Now after boxing them up, we need to find the ones that, like this one is on the edge, on the rope, right? How do we find that? Well, what we find that is we just connect them, right? What if there's something here? Hold on, because everything is integer, I think we don't have this problem. Let me draw it out. So, because everything is integer, and from 0 to 100, everything is integer, right? Therefore, would it happen that there will be something that's like, no, I don't think so. I don't think so. Do I have a proof of that? So what I'm talking about is, will there be a point that is not the most edge one and is also not on the line connected between the edge? between the out, let's call it outposts, right? Between the outposts, would it be possible? I mean, if yeah, it is actually. I mean, in this situation, if you think about it, if we have 1 1, right? We don't care about things in the middle. 1 1, 2 4, 1 1 2 4, and 4 2. Right? So we say this one, this one, this one, and we just remove this one. So we have these 3, right? And then we have another one, let's call it 3 1. The 3 1 will be included because 3 1 will be included on this, even though the line connecting these two don't cross this. All right, I change it. So we first examine this, 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 and this. The 2 horizontal lines and the 2 vertical lines. We take out all the trees that are on them, right? Once we've done that, can we say that there will be no more trees, right? That will be outside the ropes connecting all the outposts. Can we say that? Like if there is something outside, like what do you mean by outside, right? So if we have 2 lines, two trees, 2 outposts, we connect a line, right? And so we have done the 4 line, the horizontal and vertical, and now we're connecting the lines between the outposts. Now, the question is, it is possible for there to be a point that's to the outside of the connected line. Like we connected this, would it be possible for a tree outside that is also not the outpost? Is that possible? Maybe we can prove it. Maybe we can prove it. So what I'm trying to say is, suppose we have x1, x2, and no, x1, y1, x2, y2, right? And we have a line. How do we determine whether a point is to the outside? Well, a point is to the outside. I mean, it depends. Like if the x-axis, their x-coordinate is only differ by 1, then it's not possible. But if their x-axis differ by more than 1, and the y-axis is also differ by more than 1, okay? So let's call it 0, 0, right? And then we just pick any value. Let's call it 1, 2, 3, 4. 1, 2, 3, 4. 4, 4. 0, 0, and 4, 4. And we connect a line, right? Can we have a point outside that is also not? Yes, we can. We can have many points like that. We can have like a 2, 3, right? 2, 3 is outside. And I have another one's for 0. Yeah, like this. Yep, I find one. So we have 0, 0, 4, 0, 4, 4, and 2, 3. So it'll be like something like this. Let's go sketch.io. How do I do this? Draw your digital marker space. Alright, so this is what I'm imagining. So we have a coordinate, right? And we have 0, 0, and we have, let's say this is 4. This is 4, 0, and this is 4, 4, right? And then we say, okay, and another one, let's go 1, 2, 3, right? Okay, so here, 1, 2, 3. So let's say if these, and the last one, 2 and 3, right, it will be here. So if we say we want to find the rope, and we know this one is good, and this one is good, right? And then we find this, nothing, and we say we're going to connect these two, and boom, this one's outside. Now what do we do? What we can do is, it's like, how do we identify? Let's go back. So what we can do is let's sort, right? Let's sort based on the x, right? So we can get the first one, and we get this. We'll get lots of trees, and they are in order. So the first one we have to take, and the second one, the first one we have to take because that's definitely going to be included. Now the second column, if we have, you can imagine lots of trees, right? The second column, and among the column, we need to find the max and the min, right? So we find the max and min of the second column, and then the max and min. So for each column, we find the max and the min, and we just, we sort based on x-axis. Not really sort based on x-axis. We turn this into a dictionary with the key being the x-axis, and the value will be a list of y-axis, and that, a list of y-axis, right? So we turn that into that, and we iterate through this dictionary by key, but sorted key. So we go x from small to large. So x from small to large. So when x is the smallest, then we keep it, right? Whatever value there are, we keep it. And then we go to the second one. Basically, think about the second column, and we take the max and min. All right. So the first one would take everybody there, but the second one we only need to take the max and min because everybody in between will be considered included. Right. So we take the max and min, and then the next one, do we take the max and min as well? Good question. Good question. Do we take the max and min of every single column? Apparently, if the previous column has a bigger max or a smaller min than the current column, then we don't, right? So we keep track on the max, right? If it's max, then if it's larger than the previous one, we record the larger one, right? And then if it's small, hold on, if it's smaller than the previous one, if it's larger, but if it's smaller, how do you know if it's smaller we don't take it? We could still take the smaller one. Or what we can do, we find the outposts, right? And after we find the outposts, what we can do is we can connect them and then go, okay, we only have 2,000 or 3,000 points, right? We only have 3,000 points. So once we find the outposts, when we're talking about outposts, it's just most left, top, right, and bottom. We find them, right? And we get the edges of the outposts. Like in this case, we get this one and this one. So we get the entire thing, but then we pick this one and pick this one. So pick the most outside, and then we connect them, right? And we connect them. So it will turn into a, what's that? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Octagon. It'll become an octagon. Right? So what I'm saying is we pick this and we pick this because this is the outpost. So these two are the outposts. This is outpost, and this is actually not an octagon. This is just a triangle, right? A triangle. So once we do that, we will be able to iterate through every single thing, every single tree, and if the tree is outside the area enclosed by the shape, I mean, if we talk like generic, can we do a new one? Like if we talk generically, right? Generically, we'll have, some trees here, right? Some trees on the top, the most top. Some trees like here, some trees like here, and everything else. So what I want to do is we're going to create a shape. So we pick these two, right? Connect, and then connect, 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 and then connect. So after we make this connection, can we use a simple way to determine if some trees is inside, some trees outside? So I'm thinking about is, this is the initial way, right? But we might have some tree. Let's say I have a tree here, right? This one is missing, and the actual one we have to include this, but we don't know yet, right? We don't know yet. So we go through every single one because only 3,000 of them. Now what we do is to check if the tree is inside or outside. If the tree is outside, then we have to expand, right? Oh, but then the shape changes, right? Then the shape changes. It's possible that something that's originally is outside, but then when we change, it becomes inside. It's not trivial. Okay. Let me go back to the the other idea. So the other idea is we go, let's say go column by column, right? So this is a column, and then we pick the largest one, right? The largest one, the smaller one, and there's another column, right? And we pick the larger one, and there's no small one, so there's just one, and then we pick this column. That's a smaller one, right? And then this column. And then this column. Once we pick all the columns, but when we do that, it is possible that something will be like inside. Like if I have another thing here, right? We will pick it, and then if I have something larger, then I say, then we don't need this one. We can, but we do know that in order to do this, this has to grow. But how about here? In here, we start to decrease. Right? If I have something small here, we have to include it. Right? Do we not include this? Or we include all of them, right? We include all of them, and then we put them together. We include all of them and put them together. And this definitely is not ideal because I can just connect this to. I don't have to go through this. And how do I find that? Yeah, I can find all these points. They're just the max and the min points. So once we find that, we ditch everybody inside, which we don't need. And then we say what? Now we have the, so we can connect, right? And then the next one can connect. So let's say if the next one connect, right, and this one, if this connect is going up, and the next connect has like go like this, like the slope. If the slope increases, like the slope is the same, that's fine. If the slope is smaller, that's fine, right? But if the slope goes up, that means this one shall not be included, and we need to recompute the slope based on this. All right, so we just connect them together. So we have a bunch of points, and we have this go, that's good, the first one, and then this is smaller than previous one, that's good, and this is smaller than previous one. But what about this? What about this? So what we're saying is if I have, instead of here, if I have here, then we go, right? And then, so we're saying if we go down, that's fine, it gets smaller. And then when it gets small, it goes down, so we cannot go big. Now this one actually go big. So we'll go down and go big. So we say, okay, this one should not be included. So I recompute these two. Okay. Let me just think. So let's say we have this, and so we go down, right? And then boom, somebody's here. Boom, go up. So if we like keep going down, and something boom shoots up. Now when I shoot up, who should be kicked out? It's a good question. Who should be kicked out? I'm gonna go back. So if we record all the slopes as we go through, right? If we record all the slopes that we go through, and then let's say this one is connected to this slope, right? So we know, oh, it's bad because the previous slope, that's the previous slope, right? This is first slope, second, third, and fourth. So the previous slope is very, very big, negative, right? And then we suddenly go positive and then go big. So we know, oh, that's no good. Now, if that's no good, then what we do is we have to go to the previous slope, find the point, get this one, right? Now, if I have a down up, right? If I have a down up, or up up, right? If like any type of concave, if we encounter a concave shape, which is just two consecutive slopes. The second slope is, if the first slope is a negative one and the second slope is bigger, that's a concave. If the first slope is a positive one and the second slope is bigger, then that is a concave. So whenever we find a concave, right, this is a negative and it's something bigger. And then this is a positive, something bigger. We can also say this, right, is a positive, that's something bigger, right? And this is negative, that's something bigger. So whenever we have something bigger, a bigger slope than the previous one, if we have a slope bigger than the previous one, then that indicates. And also, because like from this transition, we go down, right? That's a negative, and this is a positive. But it's a positive, and also the x-axis goes in, right? It's not on this side positive and getting bigger. It's on the other side getting bigger. So if it's on the other side, then we are still doing well. So whenever we encounter a concave shape, we will eliminate the previous dot, eliminate the previous one, and connect this with this one. We'll connect these two. We'll connect the previous one. So we'll connect. And after connect, we're going to do the same thing again to compare to the previous slope. If it's still bigger, then we have to delete and then redo it until we do not have the same problem. Okay, so let's go back here. Well, the next question is, there's no next question. We just go through, pick out the ones at the edge, right? We pick out everything on the edge, and then we connect them, connect. Oh, wrong. Reconnect. Good. Connect. Right. Always be getting smaller. Always getting smaller, and oh, we also will have the problem of infinity. Dear me, how do we handle infinity? Well, we can handle infinity by try except block, so it can make our logic easier. So we'll handle the infinity by checking for 0. That's fine. Infinity is fine, right? And then, yeah, everything is smaller. Infinity is the biggest, so everything will be smaller than infinity. Unless you go from this to this, right? This will be a small and it become big. How do we handle that? So it's a small, even smaller, right? It's a small, negative. It's a negative infinity, right? That's the most small, but we can also call it positive. Anyway, so from here, and here, infinity, and then boom, we get big. If it gets big, it has to be, if we get big, right, it has to be, on x-axis, it has to be smaller, okay? And then we get small, and then we'll get big, right? If we get big, then the x-axis has to be smaller. No. From this side is we go this, right? We go this, and we get smaller. And if we get big, then that's a problem. But if we get big, right, and then if we go this from, oh, that is the issue. From this, yeah, I'm drawing the mental image. So we go small, right, and then we get big, right? We go big. That is a concern. So remove this, right, and then keep going, and then we will get. That's also getting small, right? That's getting small, or we will go this way, which is also fine. All right, let's give it a shot. I think I have an idea. Oh, this one is, I think it took me a while to even come up with an idea. All right, so here is what I'm thinking. Outer trees. All right. So first of all, we are going to default dict. And then for columns, right? So for columns, I get all the posts. Yeah. So here's what we can do. We're gonna say default dict. That would be easier. It's just a another default dict. So from collections, and import default dict. So it would be outposts equals the default dict, the lambda, right? And then return a this, right? We just want a list of two values. The first is going to be the small, the second is going to be the last, the bigger one. Actually, no. Because if it's here, I want to record every single one, not just the bigger one. Let's just do list. Simple, easy, straightforward. Just do list, right? So let's just say for x, y in trees, right? So this will give us x coordinate and y coordinate. We can say outposts x dot append y, right? And once we're done, what do we do? Well, what we do is the only thing that needs to concern is the first and is the leftmost and the rightmost, right? That's the only two things we need to concern. So all we're going to do is for each column, right, we're going to find the top, the max. Okay, max. When do we connect the max first, right? So we go left or right. We connect the tallest things first, right? Once we're done, we do the bottom. And then we connect on this. There we go. I think this is a viable way. So we're gonna say for x again in sorted. Let's go sorted once. So outpost. So sorted x's equals sorted outposts. Then for x in sorted, we can do it simultaneously. So we don't have to save another variable. So let's do this for x in sorted outposts, right? So we're gonna go to the top. How do we go to the top? So we find a max, right? So max y equals max outposts x, right? So we find a max, and then what we need to find is, so it's going to be going whatever, right? It's going to be going whatever. How do I know? Because it can go up, it can go down, right? And we want it to always go small. So we can say the top k and bottom k equals, let's say import math, right? So top k we say equals math.inf, and the bottom will be math.inf. Both are math.inf because we're starting from this position here. We just say the current slope is infinity, right? So the next one would definitely be smaller, right? So we say max y is equals to this, and min y is equals to this, right? Outposts x. So we get a max and min, and then we need the previous max and min. We need the previous slope and its value, right? So actually top k, it should be top k equals to, this is a slope, right? We have a slope and we have the slope and the previous value. We can just call the previous value as -1 because it doesn't exist. This one's the same, right? That's that. That's going to be -1. So we're going to look to check the previous slope. And we say if top k, the previous slope is equal to math.inf, right? If previous slope is infinity, then we add the current one, no problem. So we just say top k dot append, right? Append the current slope and the current y value, which is max y. Oh, actually, no. This one will be... Huh. Alright, here's what we're going to do. Turn this into this. Right? Turn this into this, and we're not going to check the top k. We just check... Yeah, -1 is not possible because they all are larger than 0, so we know this is the starting point. I just check for this. If this is equal to -1, then we simply do top k -1, 1 equals max y, right? And then else. So top k, this is not the first one. If it's not the first one, then I have the new else. Now we're going to compare the current slope, right? So the current slope, just a slope. So slope, so top slope will equal to, holy guacamole, we cannot compute the slope just by the y. We need x as well. Therefore, well, we do have x, right? So, oh my, this has to be x and y. It has to be x and y. This has to be x and y, right? So we find the max and min, but we have the x. So we're going to say 1 is going to be x, and top k -1, 2 is going to be y, the max y, right? Else top slope is going to be the current, so we're going to be max y minus top k minus y is 2 divided by divided by current x minus top k minus 1, 1. So that's the current slope. Now when we get the current slope, we're going to compare. We say if top slope, right, is smaller or equal, equal to top k minus 1, 0, right? If they're the same, now we added it, right? If they're not the same, so if they're the same, now we say perfect, top k dot append. So they're smaller, so we always be going smaller, right? Always be going smaller. So if it's always going to go smaller, Then what we're gonna do is we're gonna append a new thing, right? We're gonna append a new thing, which is the top slope with the current x and max y, right? Else, if the top slope is smaller, right? If it goes smaller than the previous one, if it goes smaller than the previous one, no, if it goes bigger, not smaller, if it goes bigger than the previous one, then we have to pop the previous one and do the same thing again, right? Therefore, there has to be a while loop. Let's just say while true, right? It has to be a while loop. Did I spell while wrong? Wait, did I spell while wrong? Huh. I had some syntax error. Anyway, so true, if this, then we can break, right? Else, we're gonna say top k dot pop, right? Top k dot pop. So the slope associated with gone, and then we have the previous one. Then we do the same thing, right? Now we compute the slope again. But then at a certain point, because the initial one has the slope, initial one has the slope, I already handled it here, which is infinity, so this will definitely pass. So while true, we do this, and we pop until one time it's good, then we continue, right? And wait, why is while? If, else, while true, slope equals this and this. Yeah, I don't know. What is the problem? Wait. Oh, else and while true. They don't have to put them together. I mean, what we can do is we can continue. Nah, something is not right. I don't understand. We have max min, we have sorted. Oh, I see. This is the problem. There we go. There we go. Now we're talking. So else we do this, and we're gonna do the same thing for the bottom as well. Right? So I say all these top k will become bottom k. Again, if bottom k is this, and we can do this, and this max y is going to become min y. And again, while true, the bottom slope, so bottom slope, right? The bottom slope will be and if bottom slope is smaller, well, actually, bottom slope shall be getting bigger, right? Bottom slope shall be getting bigger. If bottom slope is bigger or equal to, now which means for the bottom slope is going to be negative infinity, then we add it immediately, and this is going to be min. Otherwise, and then we break it. Otherwise, we're going to have to say, we're going to pop this and keep going. So we're going to do 2 rounds, right, for the top and the bottom. So we're going to add everything into the slope. All right, that's what we're going to add. We add everything into the slope. Now when we're done, we're going to have a top k and a bottom k, which contain all the coordinates. That's spanning the top and spanning the bottom. Now once we're done with that, we just need to add the extra ones on the left and right, then we should be done. So what we can do is we're going to return, right? Return this plus outposts. Outposts. Min outposts plus outposts max outposts, and this will just become xy for this x y in top k. Oh, we are counting extra one. Holy guacamole. Yeah, we need to we go to the last one, we'll take the max and a connect, right? So we need to pop them. Shoot. So which means has to go from 1 to -1. So we're going to pop the front and end. So we're going to do this and this, so that's going to be bottom k, and this and this. That's very convoluted. Alright, so here is an example. Alright, example here. The results will be this. Alright, second example. Yeah, I don't have a good feeling about this. I think we will miss some edge case. Basically, it's the same thing, right? 1, 2, 2, 2, 4, 2. Right, so our input trees, and this one will be outer trees. And then let's do sorted equals sorted. Probably need to also supply key equals lambda tuple, and the return is tup 0 and tup 1, which means we are going to sort it first based on the x and then based on the y. This will make sure that the results is unique. Alright, try it. Int is not subscriptable. What did I do wrong? Sorted? Hold on, res equals this. Let's print res, then return res. Not sure where things is going wrong. Ooh, 2, 4, 3, 3, 1, and 2. That is not what we want. Outposts, minimum outposts. Okay, there are a lot of things at issue. Let's first take a look at outposts. All right, outposts. That is correct. That is a single value. Oh my. This is not how I expect it to be. I need to have the x as well. What do I do now? Well, what we can do is we do sorted axis equals to this, right? We do it sorted, and then we have it sorted x. And then on the end we have this, right? And then here is going to be sorted axis 0, and here is going to be sorted axis -1, and it's going to be this, right? And this for x in, no, for y in, and this is going to be sorted axis 0 y. Actually, I'm going to do the entire same thing here, and this is going to be -1 and -1. That shall make it fail. Answer 112033. I have 2433, 11 and 42. So I have 24. You know what? Let's do this. Res equals sorted. Yeah, let's turn it up. So it kind of make it easier. And answer equals to this. Right? And then we say res equals answer. By doing this, they're paired together. So 1, 1. I got 2, 4, 3, 3, 4, 2, but I'm missing 2, 0. I'm missing this one. How did I miss 2, 0? Did I not have bottom k? Print top k. Print bottom k. Top k is this. And bottom k, we have a 4, 2. I eliminate the how? Doesn't make any sense. And why did I get -1? Oh, -1. Yeah, that's true. So this one's infinity, 1, 1, right? What happened to this one? And this is 0.3, yeah. And we have something that's bigger than the negative, Max. Should be min. Yep, now we pass. Okay. Then, oh, what the hell? What the hell? I'm double counting. What? Top and bottom is the same. Shoot. Okay. Top and bottoms are the same. They overlap. What do we do if they overlap? I mean, when we're drawing, we probably shouldn't change anything, right? We shouldn't concern. It's just, that's fine. And we draw. And after we finish drawing, and it came out, oh, okay. I mean, the easiest way is just to use a set. How can we use a set to weed out the repeats? I mean, these two will not have. Don't be so sure. These two can have overlap as well. Okay, let me think. What will be the easiest way to handle this? Well, I think the easiest way to handle is if we use let's try that. Let's try complex number. I like to use complex number, but I forgot again. Because complex, so right, so let's say A equals 1 plus 2j. That's fine. B equals 3. Can I say C equals 1 plus bj? No. How do we initialize complex number? I forgot. Complex number. C math. Face, polar. I don't really need. No, that's conversion from polar to coordinates. It's not what we want. I want complex number. Real dot I can put the conjugate as well. I have an example. Oh, I think it's times 1j. B times 1j. Yep, C dot real and C dot imagine. Yep, here we go. So it's another way to handle this. So this one, let's just call it -1. Right? I'll call it -1. And then blah blah blah. If I say -1, 0, no 1 is equal to -1, then I say -1 equals x, right, plus max y times 1j, right? Continue. In this case, I do think we need to write a function. Say def connect self. What do we need? We need the what do we need? We need slopes, right? Which is going to be a list, and we need current x and y, right? Slope and current x and y. And we're not going to return anything. This one doesn't have to return anything. So all we do is, while true, right, basically the entire of this thing. Right, so the entire of this. The entirety of this, we'll say while true, top slope, and also we need a Boolean value, is top. Alright, that's a Boolean value. So slope is going to be, that's just going to be y minus alright, so pre-x, right, pre-x, pre-y is going to equal to slopes minus 1, right, 1 dot real, and slopes minus 1, 1 dot imagine, right? So the pre-x and pre-y, and then this is going to be pre-y, and this is going to be pre-x, and then I say if it's smaller or equal. Hold on, how do we handle smaller and equal? I think I need to say or slope of math dot is close slope and slopes. Actually, I don't want slope. I just call it k. We can now say this is a k, right? And this is just going to be slopes minus 1, 0 if it's smaller or equal to, or it's close slope minus 1, 0. If these two, then we can call slopes dot append k and x plus y times 1j. Right? We just append this thing, and we break, and we return actually. Otherwise, we're going to say slopes dot pop, and this is where we differ if it's top. So, how do we combine? If it's close, right, then alright, so let's do this. If it's close, or right, or is top and this, or not is top and this. But hold 1 second. So if I import math, right, math dot is close, 1 and 1. I return true. So we don't have to equal, right? It means if it's on top, then we have to be, the current needs to be smaller. So smaller, smaller. And if it's the bottom, the current shall be larger, larger, and larger. So that's the requirement. So if blah blah blah, then we say this, else we pop. And then we can just say, if it's this, we do this. Else, we're going to connect. That's going to be top k, right? And we need x and y. X max y, and its top is true, right? It's on the top. And then if it's this, then we run a self.connect. This one's going to be bottom k, and then x and min y, and it'll be false. This has to be self, right? So once we're done, right? Now what do we have? Now we're gonna do this to get everybody, right? And have to put that into a set. That's the whole purpose. We put that into a set. How do we put into a set? We just say top, bottom will equal to a set, right? A set of what? Set of this and this, right? Set of top k, right, 1 to -1, and then everything we're just gonna get xy, right? It's gonna be xy, so it's xy, right? And this is the same thing. This is gonna be xy for xy in this, right? And then we concatenate them together and turn it into a set. So we're removing the duplicates, and eventually we're going to return, right? We're going to return this and plus this and this, right? And this is just going to be everything inside top bot set, right? So I'm going to say for xy in top bot set, I'm going to say this xy dot real, xy dot image, and they all have to turn into integer because they're not. They turn into a float. If we run that, I have a list assignment. Of course, it has to be this. So it has to be bottom k minus 1 equals x plus min y times 1j. Okay, run again. Slope is not defined. What do you mean slope is not defined? Oh, there's no slope. That's k. It's top k. Yeah, that's k. Yep, there we go. Alright, I'm not confident. Alright, we can run one more test case. Like the ones I can think of right now is column, like just the full column of, let's just say 1, 1, right? And then 1, 2, and then 1, 3, right? And this shall give us exactly the same result. And no, we do not. Everything is duplicated. Huh. Alright. Alright. Alright, this is what we're going to do. I'll put everybody inside. Right, screw this. Right, screw this. Yeah, because I got 2 1s, 2 2s, and 2 3s. Yeah, that's true. So what we're going to do is what we're going to return. And this plus this, I just plus these two, right? So plus this, it should be not a this, this plus y times 1j. And this is the same. It should be this plus y times 1j. Can we just do it here? What if we just say y times 1j? If we say y times 1j, so this just will be so we just say x plus max, oh, max minimum, no. There we go, now we pass all these. What else? A single one, right? a single tree. A single tree shall be a single tree in return. Yep. What else? Let's try the one that we thought about, which is 1 1. Yeah, I want to see what works. 1 1, 4 4, right? 1 4, and then 2 3. Yeah, 2 3. So the answer should be these 4, exactly these 4, and no change. This is not what I expect. Hold on. Maybe I was wrong. 1 2 3 4. 1 2 3 4. I'm calling 1 1. Oh, 1 4. It's actually not 1 4. It's 4 1. So it's 4 1. Well, I don't know. We're talking about 1 4. Let's do 1 4. 1 4 is going all the way to the top. 1 4, right? 1 4 be here. Then the answer shall be 1 4 without 2 3. Yeah, because 2 3 is contained inside. All right, let's try this. Wow, today is long. It's already 1 hour and 11 minutes. Submit. Pending. Accepted. Pretty slow. I can feel it. But we did pass. Alright, so the idea is that we group all the trees by their x-axis, right? Then for each column of trees, we find the top and bottom tree. We want to draw a top fence and bottom fence to include, right, to include all the trees. The left include all the trees. When we draw the top line, the top fence, we iterate on the x-axis from small to large, and each new line, and if the slope, right, if the slope of the new line, is larger than that of the previous line, we have a concave case. Thus, we pop the previous tree and try the same procedure again until the previous slope is bigger than the current one. Similarly, we draw the bottom line and require that the new slope must be bigger than the previous one. After drawing the top and bottom lines, the left and right lines are trivial as they consist of all the trees with the smallest not small, but the min and max x axis. The final piece is to avoid duplicates. To do that, we turn all the coordinates into complex numbers, and use set to eliminate duplicates. All right. Well, each outposts are visited once, so it depends on how many outposts do we have. That's a good question. If you have a random number of dots, how many are on the outposts? Well, it's depending on the x. All right, it's the x, the number of x-axis that we have. I mean, worst case, it is OM. Like if every tree is on the outpost, so the worst case is OM, right? OM. Say not larger than OM time complexity. But I'm afraid it's going to show a pretty. Ew. We're pretty good. I was going to say terrible. And what is that? 89%. That's pretty nice, right? That's pretty good. It's pretty good. And overall, it doesn't look too bad. Top K, we handle the first case, right? And then we run this. Yeah, I think it's pretty good. Look at this. And we turn everything to a set. This is just don't look at it. Don't look at it. Top bottom set. Not top bottom set. It's just res set. And then we turn the res set into results. That's it. Yep. All right. Go back here. Yeah, this one is. I don't think this one's easy. This one's like a more difficult medium question, I think. Unless the actual solution is pretty simple. Most likely, and I have encountered this type of situation many times. Jarvis algorithm. All right, first of all, hey, it's not fair. It's a hard question. We're not supposed to be hard today. It's Friday. Are we changing the norm? Yeah, like this one doesn't feel like medium to me at all. Did I just accidentally solve a hard question? I mean, based on the time, yeah. But it's not. You're not supposed to be a hard question on Friday. All right, so we have this Graham scan, monotone chain. Well, I solved it. Well, I didn't solve it in 45 minutes. I did come up with the idea though. Oh my god. Yeah, I no longer think it's beginner friendly, honestly. Oh well, I mean, we did identify. Oh wow, look at this. It's not trivial, even for them. Right? They have orientation and everything. Wow, so it is. They have orientation. Oh my God. It's not a simple question. OMN, every point. Oh, what's the complexity of these? Maybe did I got the complexity wrong again? I think, oh shoot. It is O and log n. Damn, I forgot about the sorting. O and log n because of the sorting. Damn it. All right, let's read. Jarvis. We start with the leftmost point. Wrap up all the given points considering the boundary points in counterclockwise. Counterclockwise. So go in the other direction. Every point P considered. We try to find out a point Q such that this point Q is the most counterclockwise relative to P than all the other points. Orientation. This function takes 3 arguments, P, the current point added in the hall, Q, the next point being considered to be added in the hall, R, any other point in a given point space. Returns a negative value if the point Q is more counterclockwise to P than the point R. The point Q is more counterclockwise to P than the point R. What do you mean by counterclockwise? I mean, I think what it's trying to say is just like the angle. In order for the points PQR to be traversed in the same order in a counterclockwise direction, the cross product of the vector PQ and the QR should be a direction out of the plane of the screen. It should be positive. PQ and QR. That's true. It's been calculated by the orientation function, which is oh, it's the it's not dot product. What it is? It's a cross product. Damn, how do you calculate cross product? You do times and minus. I actually don't know how to calculate a cross product. How do you calculate cross product? Cross product is this sine theta. No, that's not what I want to know. I want to know from the coordinate. Don't you have it easier? Now these just make things more complicated. Come on, just give me an easier two-dimensional cross product. That's all I want. Vector cross product. I think this is the one. Oh my god. Here we go. So, nah, this is not helping. What if I turn k into 0? If I turn k into 0, then what we have, ij will be 0. I as I itself. So we just find another I. K, oh, no. This is not happening. This is not happening. Do you have a simpler one? Alright, we'll probably watch it later. Anyway, so they're trying to say the cross product of this and this has to be negative, which means this angle is larger than 90 degrees, right? If it's larger than 90 degrees, then we say a P is more counterclockwise than R. All the points are, and find out the point Q, which is the most counterclock. I would say the Q that's the most clockwise relative to P, right? Add it to the convex hull. Further, if there exist 2 points with the same relative orientation, we need to consider the point I, which lies in between the 2 points. We may use a function in between. Finding out the point Q, we need to consider all the other points that are collinear to Q relative to P, so as to be able to consider all the points lying on the boundary. We keep on including the points in the hull until we reach the beginning point. Alright, let's see the animation. So leftmost point, Then we find everything the most. How'd you say it's most counterclockwise? Wait, how do you even find it? You have to compute this, right? You have to compute this for every single one. So we pick another one, and we have to do everything, and then find that. But compared to what? Orientation. Hold on, I still don't understand. We scan all the points R, and to find out the point Q, which is the most counterclockwise relative to P. Okay, how do you calculate again? In order for the PQ, I need to be traversed in the same order. The cross product of PQ and QR should be in direction, coming out. It should be positive. That's a counterclockwise, right? I don't know. I don't know how. Then what? Every single one and identifies here. I mean, this I can understand. Right? We have this, and then we just need to find. Oh man, this point is easy to find. This one shall just be the one with the smallest slope, right? The lowest point. Is it the lowest point? Now the smallest slope. So we have this, so we just define the smallest slope, that's the first one. And then we compute this and this, right? So we'd say this and this, and it should be larger than 0, which is true, which means this angle, we're talking about this angle has to be the, I was going to say smallest, but no, it's the cross product. The cross product shall be positive. But what if everybody's on the other side? Then nobody is positive. This is also related to the, so we're not comparing the size, right? So I think, yeah, and then we compare everything. All right, the most, blah, 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 blah. A negative value if the point Q is more negative. Oh, I just, hold on. Man, I still don't understand. This is, this times this minus this times this. Okay, orientation function. This one takes 3 arguments, P, Q, R, and returns negative value if the point P is more counterclockwise to P than the point R. When negative value if P is more counterclockwise to P than to R. Well, you can say Q is clockwise to R, and Q is counterclockwise to P. We are calculating the cross product of PQ and QR, which I don't understand what this one is even doing. You just multiply the diagonal, and then minus these two. We need help. Cross product 2D vector in 2D. Yeah, let's go Stack Overflow for this. I mean, that just means the third one is a 0, right? How do we calculate sine theta? I return all the math. Oh, jeez. Come on, man. This is not happening. I can't wrap my head around this. There we go. There we go. All right. It is. In a determinant of a 2 by 2 matrix. Is this helping? I don't think it's helping, man. Anyway, so I still don't know, but what I can say is what they're computing, I think, is this and this, right? And we do a cross product, and if the value is a negative, that just means this thing is bending more. Right? We're trying to find. I'm trying to find the next one. I'm trying to find the next one that is. I don't know. Orientation. If orientation is smaller than 0, Q is equal to I. So we find orientation is smaller than 0, then Q is equal to I. And we keep updating. We keep updating. What does that mean? And P is the leftmost. So we get the P as the leftmost, right? P is the leftmost. And then we need to find a Q. P is the leftmost. And then Q is P plus 1, which means anyone. This Q, we choose anyone. And then we go through every single one, right, to find the orientation is smaller than 0, which means hold up. I still don't understand. If the point Q is more negative, no, more counterclockwise to P than the point R. So we have a P, right? We have a P, and every time we have a P, we will just get a Q, right? And a Q would just be any point, right? Any point, we don't care, just any point. Like the next one. Right, just the next one. So we get a P, any point in Q. Then we search everything for an R, which is represented by I here, right? Which is represented by I here, is the entire thing. And then what we have is, hold on, PIQ, right? PIQ. Is that the function called PRQ? Q minus Q and R. Yeah, look, it's also different. Orientation, Q is in the middle. But here, Q is at the end. So it's different. This is P, this is R, but this is Q. So what we say is this is R, and this is Q, and we're trying to find this and this. It didn't make any sense, right? But what we can get from this is we get the leftmost, and then I was going to say I'm going to pick anyone, but actually no, we need to pick the one with the smallest, with the smallest, because you connect everybody. This is the smallest, so we connect the smallest slope. Yeah, just forget about this. We get the smallest slope. So now we do. Now we have everything. Aren't we just picking the smallest slope among everything? We just pick the smallest slope. That's the one that's not including the ones we already have. We just pick the smallest slope, and we get it, then we'll do the next one. That's actually not the smallest though. At the beginning it is, but then things change, right? Things change. So we do need this and this, right? What we want is to find the sine theta. We want to find the point that, because if we go this and this, the theta is huge. So we want to find the sine, the theta, the smallest theta, right? Just forget about all that. That's just garbage. It's garbage, the way that it's explained. What we want to do is find, so we get the smallest slope at the beginning, and then we have the original vector, and we search through every single one, right? And then what we need to find is the vector that has the smallest angle between the original vector, and that is the next point. And when we're here, then the original vector is pointing this way. And we have all of this. And I just need to find the one with the smallest, right? And find the one with the smallest. I want everybody to find one with the smallest. If, like, we have, yeah, then that's, yeah, the smallest theta. Maybe that's what this Graham scan is about. All right, let's check. Oh, that's my method. Boom, boom. Yep, I think this is my method. Positive, yeah, and then positive, then negative. Wait, then how do you determine? Oh, you use a slope. You go this way up. Ah, I see. I see. I see. So you, how should I say it? Sort everything based on the slope. So we start from the lowest slope, and then if it boom shoots out, which means if your slope shall be increasing, right? Shall be increasing. No. No. So this increase. How do you justify this? The x position? The angle? We have the orientation again. So this is angle as well. All right, let's see the angle. So and right, and these two, which is good, and these two, and then this and this. Original line comes first. First 2 points. We push the points on this line onto the stack. Or the sorted points, if the current point being considered appears after taking a left turn. Relative to the previous line. So we do. So this is the previous line. And we need it to take a left turn, which means this theta, right? So if we go this way and this way, so this theta has to be larger than 0, right? And then this is this, and this one's this. They're larger than 0 though, but it's hold on. So what we're saying is it has to make a left turn, right? So it has to be like this. But if we go a right turn, then I think what happens is if I have here, right? This is the original direction, and I'm going here. If I go this, then the sign value will be negative. Because the vector is going this way, and if it's going this way, because it's the right hand, it's the right hand rule, right? The right hand rule. So it's pointing up, so that should be a positive. So we need it to be positive. If it's a negative, then we pop the previous one. All right, let's see this. Anyway, I think I know what this one's talking about. We just need to confirm. Like after I'm done with today, I'm going to confirm on the cross product, and I think we're good to go. Yeah, I think what this one is talking about, I know. What's the last one? Monotone chain. Right to left and left to right. Isn't this feels like the one that I'm doing? They all use orientation. Yeah, what I'm doing is I find the top two, so I just connect, right? If we go here, we can use the slope, and now we pop this, and we go here, right? The next one here, we pop this. So it's all the same technique, All right. We can post ours. Monotone chain, convex hull. Yeah, we just need to find out the cross product, 2D cross product. All right, let's post ours for fun, right? For fun. So use slope rather than cross product, and consider only the top and bottom fence. I'll probably write some comments, all right? Actually, we don't need to write comments. Right. Current Let's say this is our current slope, and I'll compute. All right, so let's say use slope rather than cross product. Also, we only have to consider slopes for the top and bottom fence. Lastly, use complex number to easily, lastly use complex number to represent coordinates such that eliminating duplicates is faster. All right, now I post this one in. Then post. Yeah, I have a long thing here. All right, that'll be it. I'm gonna end this, but I will have to do a cross product thing. It's very important. I want to know. All right, that's it for today. I'll see you guys tomorrow for another difficult one. Adios.